or what we said previously is due to the condition that we have the uniform circular motion. So that means the uniform circular motion means the tangential velocity of the circular motion, which is this, have the constant in terms of speed. So the direction may change, but the tangential one have the same magnitude of the velocities. That's the reason only the acceleration happen is the centripetal acceleration. But in this case, it's for non-uniform circular motion. Rather than you have the centripetal, you also have the tangential acceleration as well. Tangential acceleration is up as AT here. And you also have the centripetal acceleration, or the acceleration pointing in the R direction. This is the centripetal acceleration, and this is the tangential acceleration. Since the direction that pointing toward different different direction, we have another way to determine, like we use in the Cartesian coordinate, to determine the direction in x and y. Whether the direction pointing toward x or not, we have I hatch as saying is going toward x direction. We have j hatch pointing toward y direction. But however, in a polar coordinate, we did say about the r and theta before in the vector chapter. But in this case, we emphasize of the unit vector or the directional vector that pointing outward from the center along r axis. We call this r hatch. This is the unit vector of r, right? Which is pointing outward from the center. If it's pointing inward, so this is going to be minus r. And theta hash here is when you sweep the theta angle from x-axis. So it's perpendicular to r hatch, so that this theta hatch pointing as a direction of theta, right? And when it's pointing, this is like counterclockwise, so it's gonna be plus theta hatch, right? If it's called as clockwise, so this theta hatch gonna become minus theta hatch. So let you know, you now introduce r and theta hash as a unit vector to tell whether it's pointing toward r direction or theta direction. So what does this mean? This means the tangential acceleration due to the change of the speed or the magnitude of velocity. This is the magnitude of v, right? It's pointing in theta direction or in the tangential direction. This is how theta hatch represent in the tangential part. This is the tangential. How about the r? As we know, the centripetal acceleration is pointing inward toward the central of the circular motion. This is still a circular motion. When this object moving like this, so the minus sign express the inward direction. So we have the first term as the AT tangential acceleration and the second term as the centripetal acceleration. Since you got the acceleration in terms of vector, you know the second law of Newton, a second law of motion or Newton law, right? This is how you get the force that from the Fr is the centripetal force, and Ft is the tangential force. This is the Ft. Right? This is how you determine force that happen in the non-uniform circular motion. So this is happen not only in one force that we learned in the previous example. This is due to the AC. We also have another acceleration, tangential one as well. And the resultant force is due to the total force, total acceleration here, which we already said about this. Now we did define the direction or the unit vector of r hash and theta hash, which is theta hash point toward the tangential. When we plus sign if it's counterclockwise, right? And r is point out of the central. It's gonna be plus sign for that. Vice versa, is point inward or toward the central, it's gonna be a minus sign. If it's clockwise, the theta hash gonna be minus sign. And this is the total acceleration is sum between the tangential acceleration and radial or centripetal acceleration. Make sure you sum it as a vector, right? Because these are all vectors. For this problem, we would like to determine the string tension at the theta angle position, which is this position here. This is what you would like to determine. But however, I just would like to explain about the overall motion that happened. So it can be on the top, on the bottom, or at some theta angle. Any position you can use the idea of the second law of Newton's. And you know the centripetal acceleration that involved, and also the mg, and this can be used for explain in every position. So what about the position at the top position? If you use the second law of Newton's, sigma F equal to ma, which is in this case is AC, you will get the total force or net force is T top plus mg, because it's pointing downward direction, equal to mac. In this case, you got T top is equal to mg. I will overwrite properly. mv square over r minus mg. If you write in terms of the mg, it can be mg v square over rg minus 1. In this case, it's similar to the previous one, but scenario is different. The apparent here is the string tension, right? How about at the bottom? You got the sigma F equal to ma in this case, which is the net force is T bottom minus mg equal to mac. So that the T bottom is the mg1 plus v square over rg Newton, right? And what happened when these have the angle theta? This is mostly look like a uniform circular motion in this case. So we do calculate on this part, and what we have seen in this pointing like toward the inside, when this theta have the angle theta here, the net force that happened here is what you have, the T minus mg cos theta, right, equal to mac, which is your mv square over r. So in this case, your T is the mg cos theta plus v square over rg here. This is how you have the string tension in terms of velocity, radius, gravitational, and the theta. Now, since we know all the force that can happen to our circular motion due to the acceleration, whether that acceleration gonna be the tangential acceleration, or it can be a radial acceleration, right? So the radial is pointing inward. This is the A radial, and the tangential is along the part that this car moving. And this is AR. So what is happening here? When you're driving a car, you will feel a force that going in different direction, which is in this case we determine the fictitious force as a result of the force that pointing in different direction of the centripetal force. So the radial acceleration here introduce the centripetal force, right? As we already know, this when the car is cornering like this, the friction introduced you to have the centripetal force. However, your body is tend to moving outward like this. You mostly knock the a shield or a window here if you turn quite quick. So this force we call the centrifugal force. Since this one is pointing opposite direction of the centripetal, but the magnitude of this centrifugal or centripetal, they are exactly the same. Fc equal to this Fc in terms of magnitude only. The direction is pointing in different direction. That is how you determine the centrifugal force, that when you feel it to the system, that it has been accelerated by cornerings. Another force is the Coriolis force. This force happen when you have different field of view or frame of reference that you observe. If you're in the guys that sits on the earth, this is the ferry wheels, the wheel that can be rotated. Right? If you sit outside of this system, when the guys that sit on the wheel try to throw this ball outward to another guy, what you see the linear motion is independent to the rotational kind of thing here. But if you in the rotation platform, if you sit on this rotation platform, what you have seen this guy throwing the ball, this guy is throwing the ball outward with some the velocity and also the acceleration at the tangential acceleration and also the radial acceleration. This influence the additional force, which is the Coriolis force, due to the change of the radial position. As a result, rather than you investigate the linear motion of the object, you see the curved motion of the object to another guy on this rotational platform, the rotating platform. This is when you look on the earth, not on the platform. Right? This is another type of force which is called the Coriolis force. We can deal with this calculation later, but now we let you know about this type, another force that influences to the change of the radial position while you in the rotating coordinate system. So let's look into this problem. This is showing how to use the knowledge of the fictitious force or the centrifugal force, but this is happen in linear. So how can you deal with this problem? This is what happened when you're in the train and the train moving on the right handward. But what happened here? There's another force that is a physicist force acting backward. This is FC, which is the FC is the centrifugal or physicist force here. Oh, we write it. Physicist equal to the force that this train moving forward, also the MA. As I said, I consider only magnitude here. Right, just ignore the vector term, because if you like to determine about the vector, you can put the minus sign in front of it. However, so look after this system. This is non-inertial observer. That means you sit on the earth and you look after this system. This system moving this direction with the acceleration. How can this lady investigate it? So with this case, you would like to determine the magnitude of the force that relates to the acceleration of the boxcar, or it can be train if I say so here. Measure the inertial observer in figure A. So this guy want to look after this one and would like to check how about the force that she can send. So let's look after this problem. This problem is covered on the idea of the fictitious force, which is this one. So we would like to investigate the thing that happened, and we can throw back and explain about thing in terms of the fictitious force. The fictitious force is what happened when you are as a person who observe in the system that moving and feeling about that force. For example, in the case of the observer A, here this lady observed on the ground. So what she have seen the motion of this object pulling like a backward and hold by the string tension. But what is she observed? In only phenomenon happen here with the acceleration that moving. But however, with the guys in the non-inertial observer, when he's on this train or the box car, I call this as a train. What he's in like he moving with the same system with the acceleration. He not feeling about the acceleration, but what he has seen, he's seen another force that pulling this object backward. This is called the fictitious force that we observe in the point of view when you are on this train that moving with the acceleration. So I will derive from the first one first. So if you apply with the second law of motion, or Newton's second law, what you have seen the balance in terms of the motion of this object. So in x direction, it's equal to ma because it's moving with acceleration along a axis. It's in like dynamic equilibrium. So in this case, if this t and this is theta, you can break a component here for x direction as t phi theta equal to ma. And how about in a y direction? That is in a stationary state. So sigma fy is equal to 0. So that you got t cos theta equal to mg. This is what observed in lady A point of view. So for this guy, when he look after this system, what he have seen the force that happen along the x-axis, which is pulling backward like this, and another force due to the tension pointing like this, because he observed this object quite stationary compared to this lady observed this system moving with the motion. So in this case, all the first law of Newton has been applied, the law of inertia. So when you observe in x direction, sigma fx equal to 0, so that you have seen, rather than have t here, we apply with this kind of the component breaking. So you have t sine theta equal to f fictitious, and your fy direction is equal to 0 as well, because net force is 0, so you got t cos theta equal to mg. Since these systems are exactly the same system, but the observer are in different type of reference, so in this case you can assume that the fictitious force is equal to ma, because this lady also observed this thing moving, and this guy also observed the same things. So that's the fictitious force is happen when you observe in the non-inertial frame of reference on a system that moving with the acceleration, and that resultant force is the fictitious force. The example is like when you sit on the car, you will feel about the fictitious force, but the person who sit outside the car see nothing about this fictitious force. This is outside, this is inside. The turning car that you have the acceleration equal to v square r when it's turn corner. This is what happened in fictitious field of view.